So we are recording now. Okay, guys, so let's go and let's start. Let me share my screen. Do you see my MATLAB? Yep, perfect. So let's go, guys, into linear algebra. Okay, so in linear algebra, let's do the basic thing of linear algebra. So let's go for what is called special matrices. Okay. One of them, for example, is what we call the zeros matrix. So if you want, imagine. No, what I have not. So it simply produces zeros. So if you write, for example, zeros 2, it's going to do a square matrix, zeros. So we are going to see how we use the zeros matrix later, okay? When we create series, for example, so we can create a matrix that is started with zeros, and then we start filling values, right? We have another one that is ones. We don't use this a lot, but it's good for you to know. It's the same idea. So instead of zeros, it fills with ones, okay? This is useful, guys, when you want to replicate matrices. Okay, so for example, if you do, I want a matrix, a 3 by 3 matrix of pi values. Okay, so what you can say is, okay, create a ones and then element by element pi. So you see, so if you want to replicate a matrix, you can do that also. Do you remember, guys, we had the rep math? This also can do the same work. Okay. Now, of course, we have random numbers. When we say run, guys, just like that, dimensions, the dimensions that you want, this one here is a uniform random between 0 and 1. Okay? The run just per se is between 0 and 1. If you want to do the normal one, it's normal, and whatever, if you want, a 3 by 3, you have that. One matrix that is really important, guys, is the identity matrix. Remember the one that has ones in the main diagonal and zeros otherwise. So the MATLAB command for that is I. Okay, so we can define two matrices. Let's do something easy. And let's define V, I don't know. Just something, oh, sorry, something simple, guys. We have done already the sum, subtraction, degree. We have done element by element multiplication and power, etc. So we know that, right? So no issue with that. Remember, guys, that in matrix operations or linear algebra, guys, we need to pay a lot of attention to the dimensions of the matrices. Got it? So when we want to sum the same dimensions, same columns, same rows for both matrices. Now, what is the rule for? Let me open Paint. Paint. So what is the rule for multiplication, guys? Do you see my screen? Are you seeing my Paint?
Yes.
Okay, perfect. Because I don't see you guys. I don't know what's going on here. So if I want to multiply a matrix A times a matrix B, so if A is m times n, B needs to be n times n. Do you agree? In such a way that you see is going to be a matrix, in this case, can be n, whatever. In this case, n times I, j, let's call it, okay? Just to make it more general. It's going to be an n times j. Got it? So just remember that as the most fundamental property. So I can multiply, of course, A times B. Tell me one thing, guys. Do you remember that 1 times 2 is, let's see, 2 times 3 is 6. 3 times 2 is 6. This holds in matrix multiplication. So what I'm telling to you, is this one here equal to A times B? No. Okay, so matrix multiplication, guys, are not commutative. in general, okay? There are some specific, some general matrices that is true. So A times B is different from B times A. Okay, just remember that, non-commutative. Let's go back to here, and you can see that. You just run this one here, and then you have completely different numbers. Now, can you show me, guys, that what I'm writing here is true? Just to, let's use the A and B. We know that there is an identity matrix, so this is called a unit matrix. Do you agree? Why? Because remember, it takes the position of the unit unit number. Any number multiplied by 1 is the same number, correct? So in matrix multiplication, I is that 1. So this means the following. Can you show that A times I equals I times A equals A? Just using the matrices that we have provided.
Sorry, I is a identity matrix or is it a vector
Yes.
of both? Okay.
Yeah. This one here is my identity matrix. So remember in MATLAB, this is the famous I, right? So basically here, guys, A times I. Oh, I can define I of 2, right? And let's take a look to I. Or we can do I of 2 times A. We go to the same equation, to the same matrix. Do you agree? Now, there are certain operations, guys, that we love in econometrics. Let's assume, guys, let's define U equals 2, 3, 5. So this is my matrix. And this is U. Can you check what is U prime U and what is U times U prime? First of all, when I do this stuff, U prime U, let me define U in a different way. Okay, let's define U as a vector. Normally we have this as a vector. Sorry, as a column. So U is going to be basically like that, right? 2, 3, 5 is going to be 3 times 1. So when we do U prime U, it's going to be what, guys? It's going to be 1 times 3 that multiplies at 3 times 1. So my result is going to be a 1 times 1, correct? This one here is called an scalar product. Scalar multiplication. Okay, just some names. And this one here, guys, is called a quadratic multiplication. Take a look. So this one here is going to be 3 times 1, 1 times 3. So my resulting matrix is going to be a 3 by 3. And this matrix is called a quadratic multiplication. You're going to see in a minute why. So my U is 235. Right? So now my U prime U, U prime, is 38. Do you recognize this number here, guys? You know what we are doing in this case here? And this is useful for OLS. So take a look. What I'm doing here, where's my mouse here? What I'm doing in U prime U, so U prime is going to be 2, 3, 5. That multiplies 2, 3, 5. Do you agree? So this is element by element. It's going to be 2 squared plus 3 squared plus 5 squared. Do you recognize this one here? This one here, guys, is the sum of U squared. Okay, and why this is very famous, guys, because normally what we do in OLS model, ordinary least squares model, is simply we try to minimize the sum of the square of the errors. Do you agree? Okay, so this is something that you need to pay attention. If you have one matrix and you do U prime U, you are doing the the sum of the square of the numbers. Make sense? Okay, so what happens when you do u prime, u prime? So let's do u times u prime, u transposed. What is particular about this matrix, guys? This matrix here, guys, resembles very, very, very strongly what is called the variance covariance matrix. Okay, remember the variance covariance matrix. So what are the main diagonal here? So why the name of variance covariance matrix, guys?
Because the diagonal essentially is the uh I'm blanking. It's the variance is the
Yeah, it's a
diagonal.
variance.
Yeah, yeah.
Exactly. Take a look, guys. Take a look to this 4. This 4 equals 2 squared. What is this 9? 3 squared. What is this 5? 5 squared. Do you see? So what the components in the main diagonal, guys, are the variances. And outside the main diagonal are the covariances. Got it? And remember, this is a symmetric matrix. You have 6 and 6, 10 and 10, and 15 and 15. One interesting thing, guys, is that how do I get the elements of the diagonal? Okay. Well, there is a MATLAB command that is called diagonal. Oh, I need to give a name. Sorry, let's give a name to this one here. Okay. Let's call it Q. Okay. So diag of Q is this one here. So the diag command allows you to basically remove the diagonal elements and put them in a vector. Let's call this D. And if you have a vector, guys, and you use the diag, what it does, it puts the vector into a diagonal. Do you see these two examples here? So if you take the diagonal of a matrix, what it puts is in a vector. Okay. Then if you have a vector, you want to put this in the main diagonal, you simply do diag, the command is exactly the same. Got it? Okay. So let's go to some properties of some matrices, guys. So let me write one matrix for you. So let's do 2, 3, let's say 6, 9. Do you remember the concept of singularity? When a matrix is singular. Okay, so now let's go and talk a little about the determinants. All these things are useful for the OLS model, guys, okay? So what is a determinant, guys? So before this, let's go to this matrix. 2x plus 3y equals 5. 6x plus 9y equals 15. Okay, so I have two equations, two unknowns, correct? Do you remember how to solve this model here, guys? What you can do is you simply do matrix ways, 2, 3, 6, 9, that multiplies x and y, and this is going to be equal to 5, 15. Correct? So the solution to x and y, it was a Kramer method, remember this stuff, but indeed is equal to 2, 3, 6, 9 to the minus 1 that multiplies 5 and 15. This one here, guys, is the adjust, so I will call this matrix A. It's the adjunct of matrix A divided by the determinant of A. This is the definition of the inverse. Got it? And if the determinant is different from 0, so this matrix is called matrix A is non-singular. So why non-singularity is important, guys? Because take a look, this is a simple ratio. Do you agree? This part here. If the lower part equals zero, so if the determinant of A equals zero, what happens with the answer here? It's going to be any number divided by zero,
Zero,
uh,
infinity,
undefined.
undefined.
Undefined. Okay, so that's why we always look for non-singularity. So how do we check for non-singularity, guys? Simply take a look to the determinant of A. Got it? And so that's why the determinant of A is so crucial. Got it? Now, tell me one thing, guys. Can you solve this equation? We have remember the rule is I have two equations, two unknowns, so I should be able to do that, right?
No, this is not linearly independent.
Independent.
Yeah.
However, guys, exactly. Exactly. However, in order to solve a system of equations, the system must be linearly independent. So you can take a look, guys. What I have done, this one here, is simply 3 times the first one. So indeed, we don't have two vectors. We have one vector. So we have one equation with two unknowns, infinite possible solutions. Got it? Of course, this was an easy example, but how do I know that indeed this matrix A is singular? How do you test that?
Calculate the determinant.
Exactly. And the MATLAB command for the determinant, guys, is simply DET. DET. Okay, let's do that. Can you be doing that while I save this part here? Okay, so let me go to here. Okay, so let's take a look to the determinant of A. 0. It is non-singular, so the system of equation doesn't have a solution. Make sense to everyone? Okay.
Sorry,
Now,
just to confirm,
yes,
determinant A not equal to 0, then it is not singular.
right. And we
Okay.
want that. And we
Okay.
want that.
Thank
Okay.
you.
So in this case, we want non-singularity. Let me check if yeah, can you copy this one here, guys? This equation here, sorry, this matrix here. I sent you one Word file with some help for tonight's class. So can you copy this matrix A into MATLAB? And I will print it. Do you have it? Okay, so what I want from you is the following. Let me move this somewhere here. So I have my matrix is going to be, yeah, my matrix is going to be 2, 1, 3, 4, 5, 6, 7, 8, 9. Okay, can you check the determinant of this one here? So if you use the determinant of this one here, I think it's big A, caps A, I don't know. So what is the determinant, guys? 9?
-9.
Oh, -9. So as soon as this is different from 0, so A is non-singular, and the inverse of A is going to be, well, the inverse of A applied to an equation is going to provide a unique solution. So basically, I'm saying this one here. This one here, as soon as the determinant is different from 0, it will be well identified, so I will get unique solutions. Make sense? So some properties of the determinants, guys, and I want you to tell me what happens. Show me that this one here is exactly the same as this one here. Show me that indeed, let me see. So this was my A. No, my A. Yeah. Can you create B, guys? And I want B to be the following. I want 1, 5, 8, 2, 4, 7, 3, 6, 9. So what I have done is I have switched. I switched these two guys. Okay, don't type the numbers. Do the flips or do whatever. Okay. And once you have done that, take a look to the determinant of B. What happens? Let me know the determinant of C. What's in nose? Let's do rows, much easier. And then determine. One minute to do this, guys. Resume recording. Okay, so let's do the first one. The first one is easy, right? And let me move my figures here, the image here. So the determinant of A prime is goes exactly the same. Correct? So the next question requests you to create V, simply shifting the columns. Okay, many different ways. So let's call this V equals it's going to be a matrix, right? So I can say from A, all rows, second column minus 1 to 1, and then simply add A, everything, comma 3. Well, it should work or not? So what I'm doing is I'm shifting here. I'm selecting every single row, start at 2. So it's going to be 2. And the next one is going to be 1. And that's it. Correct? You can have different fancy ways of doing that, but just try to do this type of matrix manipulations, guys. It's going to be extremely useful. Okay. Very two examples, but you're going to be seeing that data is exactly the same. You have huge data sets, it's exactly the same. Okay, so now what is the determinant of B? So this is another property of the determinants, guys. If you shift the columns or shift the rows, not both at the same time, okay? So if I shift columns or shift rows, the determinant is going to be exactly the same. And remember, guys, do you remember this property on all S models? Everyone here has taken econometrics, right? Okay, so remember that there is one thing that the people believe. Imagine I have Y as a function of X1 and X2, okay? So they believe that changing the order, so the X1, X2 should be different having X2, X1. That's completely false. Okay, it doesn't matter. In OLS models, in linear algebra, it doesn't matter the order. Okay, and the determinant is one of them. So you shift columns or rows, okay, nothing changes. Got it? Remember in this case, the only thing that changes is the sign. But in the global operation, guys, you see that also the inverse is going to change, so everything stays the same. Got it? So let's go to the next one. So what was the next one? Create C. The first column multiply by 5. Okay, so let's create C equal A first, just not to destroy our A. And what I want is C, it was the first column, guys. I said first column.
Yes, first column.
Okay, first column multiplied by 5. Oh, then I need to have my C. Oh, C. Okay, so how do I do this stuff? I want the first column to be multiplied by 5. This is my C. How do I do that, guys? I know that if I do this stuff, I simply create something artificial. So what I will do is going to be C, okay? Sorry, C of everything, comma, what was that? Everything, comma 1 is going to be equal to. So I'm saying this one here is the one that you need to replace with this one here. Make sense to you?
Mhm.
Okay, so this is important, guys, because sometimes you want to change something. You need to first call what you want to do, where you want to work, and then you simply replace this with whatever you have. So I have here my 10, 20, 35. So if you compute the determinant of C equals what, guys? When you multiply one column or one row by a constant, your determinant is multiplied by that number. So remember, your determinant was -9. I have multiplied the first row by 5. So it's going to be multiplied by 5. This is -9 times 5. Got it? In general, I think that the next question is a generic question. So now I want everything multiplied by 5. So where is my MATLAB? I want, it's going to be D. Okay, let me call D equal A. And then I want D is going to be equal to D and multiply by 5, correct? So now what happens with the determinant of D? It's just yes. What is this number? 1,125. Indeed, this one here, guys, is equal to, this is not obvious, it's rank of A, rank of D to the power 5 times the determinant of A. Sorry, it was D, determinant rank of D. Let me check what is this rank. Oh yeah, by the way, the rank, what is the rank, guys? Oh yeah, I know. No, it is my number to the rank. Is my number to the rank? Yes, it's my number to rank. Yes, now it should go. So what is the rank, guys? I'm using this opportunity. What is the rank? The rank is the number of independent columns or rows. Got it? So this is another way of seeing a non-singularity. So if the rank of your matrix is exactly the same as the number of rows or columns, for example, so this implies that they are linearly independent. So this implies that the determinant is going to be different from 0. Got it? And I think we have one last property. What last property is that? Yeah, I want E. Okay, so let's define E. So let's define E equals A. And then what I'm doing here, guys, is what E of everything. No, I think it's what I told you. I told you what, guys?
I forgot.
Yeah. It is adding, what's that? Oh, first row times the second row. Adding that one. So let's take a look here. So is first row or columns is going to be equal to what? The first row is this one here plus 2 times the second column, correct? No, the second row I'm talking. Do you agree with me, guys? So this one here is going to be, I'm saying, replace from the first row, all columns, or the first row, all columns is going to be equal to the first row plus 2 times the second row. Make sense?
Do you mind just clarifying what you did for 2 again? I'm still kind of
This
confused.
one?
No, just a question 2.
Which one
Yeah.
is question 2? Let me check.
Yeah.
This one?
Yeah. I'm just kind of
Oh,
confused. Yeah, because I did
yeah.
it a different way, but I just want to understand how you did it.
Yeah. What is this one here? This one here. So I said, okay, B is going to
Mhm.
come from A. So what I have done
Yeah.
is I have shifted first the second to the first. Do you agree?
Shifted the second row
Yeah, the second
to the
column.
first.
No. I'm talking about columns. All the rows,
Yeah.
second column.
Yeah.
Okay, so it's going to take first this number here, this column
Yes.
here.
Yeah.
And then in the loop here, sorry, in the sequence here is going to be 2. The next one is going to be 1, correct?
Yes.
Because it's 2 minus 1. So then it's going to be all rows, first column.
Yeah.
Okay, so this one, the first part is simply shifting the first 2 columns.
Okay.
And then I'm simply putting together the third column.
Oh, so the reason why you like essentially that A colon comma 3, that's like
Is this
saying
one.
like
Just
that's
keep,
our set column.
yeah,
Keeping that.
exactly. Just keep it
Okay.
there. Keep it there.
And just to make sure this matrix form is essentially the comma is saying that's the next column.
Yes, of
Okay, that's
course.
what confused me. Okay,
Of
thank
course.
you.
Of course. So remember when you have commas, you're putting next to it. If you put semicolon, you put below that. It doesn't matter if it's a number or if it's a vector. Make sense? The
Yes.
comma is put next to it, semicolon below.
Perfect. Thank you.
My pleasure. So now what is the determinant of E? nothing happens. So this is your property, guys. So if you simply sum multiply one column and you add to or add or subtract to another column, nothing happens. The thing is you need to do column, column, or row, row. Okay, you cannot do two things at the same time. You cannot do that. For example, I cannot do 2 times the second column minus 3 times the third row, for example. In that case, no. Okay? Make sense to you guys? Okay, so now let's go and let's continue with the inverse. So you see, guys, that the inverse is the one that allows us to find solutions. If we don't have an inverse, because my determinant is 0, so this implies that my inverse is infinite. So this implies that I have multiple solutions. Got it? So we know the determinant. Let's go and see how the inverse works. The inverse is very simple. Let's call back my A. And my inverse is that the MATLAB command is inverse of A. That's it. Or if you want, A to the power minus 1. It is exactly the same. Okay, now you prove some concepts. Okay, are you with me? Okay, so some properties now with let me clean this stuff. Okay, there are some properties, guys, in the inverse of matrices. A times A inverse should be equal to A inverse times A, and this should be equal to unity, identity matrix. Can you prove that, please? Another property, guys, is that A prime to the minus 1 is exactly the same to A to the minus 1 prime. Okay, can you prove this too?
Professor, just a general question. If I turn on bank format bank, how do I turn it off? I tried to look it up earlier.
Oh, format
Yeah.
long.
Okay, thank
Format
you.
long. Simply you go back to the default in MATLAB is long. Remember, the MATLAB guys are engineers, right? So they like all the precision as possible. In our case, 2 decimals is perfect. Bank for us is good, but if you want long, it's long. Make sense?
Thank you.
Pleasure. So now let's go and see see this one here. What I was telling to you. Okay, so inverse of A times A. Do you see the identity matrix? Or A times the inverse of A is the identity matrix. Make sense? So now let's do the inverse of A prime. And let's do the inverse of A prime. And let's do inverse of A and all this prime. Do you see that? Perfect. Okay, so now let's go back to my previous example. No, let's go to the Word document. Yeah, I want you guys to write this system of equations. Okay, you have, so this is the equations. I buy 1 apple, 2 bananas, and 3 oranges. Okay, X1 is bananas, oranges, sorry, no, apples, bananas, and oranges. So X1 is apples, bananas, and oranges, and I pay 366. Okay, so model this one here, guys, in terms of a matrix. Okay, allow me let's do this. Is 1, 2, 3, 4, 5, 6, 7, 8, 0. Yeah, okay. So what I'm saying is the following: is x1 plus 2x2 plus 3x3, 4x1 plus 5x2 plus 6x3, 5, 6, 7x1 plus 8x2 plus 0x3, and this number equals, allow me to check this again, equals 366, 4, 366, 804, and 351. Okay, so that's the system of equations that I want. Is what I want to find basically, guys, is how many apples, bananas, and oranges that we have bought. Got it? So in matrix way, also I have a, give me 1 second. Let me add this one. So this a matrix way, guys, this implies the following. So I have 1, 2, 3, 4, 5, 6, 7, 8, and 0 that multiplies x1, x2, and x3 should be equal to 366, 804, 351. Okay, so build this matrix. Let's call this A. This is going to be X, and this is going to be B. So X is going to be equal to what? It's going to be simply A to the minus 1 times B. Correct, guys? Okay, do this first. And indeed, the mathematicians use a different notation that is a different method, guys, technically. This one here is said to be more efficient. Okay, when you have huge matrices, A to the minus 1 can collapse your computer. This operation here, backslash operation, is exactly the same as this one here, but this one here is more efficient. Okay, try and tell me the values of A. You get the values? Okay, 1 minute. I will stop recording. Okay, guys, so my A is going to be equal to 1, 2, 3, 4, 5, 6, 7, 8, 0, correct? So this is my A. And my B, remember, guys, that the dimensions matter, okay? So my A is a 3 by 3, so my B needs to be a 3 times 1. Otherwise, you're not going to be able to operate that, correct? So my B is going to be equal to, what was that? 1 second. 366,804. It's going to be 366,804 and 351, I think. Right? So my X is going to be simply what? It's going to be the inverse of A times B. Done. Make sense to you guys? Perfect. Okay, so now if we do, let's call this X1 is going to be equal to A backslash B. You see, there is no difference. Okay, however, if you see the speed, it's almost nothing. The one that is faster is this one here, guys. I remember I had a mathematician friend when I was doing my PhD, and I was having a huge problem with inverses of A. I was using, I think it was 200,000 rows by 250 columns. So it was a huge matrix. And a computer, well, the computers were not as powerful as the ones that we have now, but the computer simply collapsed. And I was simply frustrated because I cannot partitionate the matrix to find the inverse. I need to have the complete matrix. And this guy came and gave me a beautiful explanation why this was much efficient. Of course, I forgot the explanation. But the thing is that indeed it worked. Okay, so it really worked. Okay, so now let's go and talk about the specific issues that we have when we have this system. These are called systems of equations, right? You remember that? It's high school. This is called system of equations. Okay, so now let's go. Let me move this one here, somewhere here. And let's do a couple of things. So imagine, guys, that you don't only have this one here. So you have this one here. So let me, something that is called over-identified systems. And then this also happens in real life. So let's assume, let me tell you, I will just do the matrix, okay? So imagine that you have one additional piece of information, 3, 4, 5, 6, 7, 8, 0. And imagine that you have 6, 5, 9. So you have one additional piece of information, this one here. But you still, and then you have your B, sorry, this is your A, your X is going to be equal to 3, 6, 6, 8, 0, 4, 3, 5, 1, and then let's see 5 to 5. Okay? So what happens in this case, guys? Why is called overdetermined or over-identified system? Because I have 4 equations for 3 variables. Indeed, mathematically, guys, I just need 3 and 3, correct? Linear independent equations. Now, the way you solve this one here is you try to minimize the sum of the square of the errors of the system. So the way you solve these systems, you minimize the sum of squares of ax minus b equals 0. So that's what you try to do. Got it? And in MATLAB, this one here translates simply into doing something we have done already. AB. Okay, so in MATLAB, let's create. So this was A. This was B, correct? So let's call this A1 so that the overall matrix A1 and the overall matrix B is this one here. Can you create A1, B1 and just do this and see what happens? Am I recording? Oh, yes, I'm
Yes.
recording. Yes. So create A1 that is going to be a matrix, right? That contains A, and then just below that, write the numbers that I wrote here. Two minutes to do this, or I will stop this one. I need to repeat this stuff. So while you do this stuff, I will repeat because I was not recording. So we were talking about under determined systems. So basically, when I have less number of equations than variables, like in this case, A2 is simply the first 2 rows of A, and B2 is simply the first 2 rows of B. There are 2 ways of solving this one here, is simply A2, B2. And remember that when we have undetermined systems, we have infinite solutions. If we do what we have been doing up to now, some of the x's are going to be 0, simply 0. However, we can do a new methodology that uses the P inverse of A. And what it does is simply minimizes the Euclidean norm of a matrix AX minus B. Got it? And this is the most efficient way. This is a better way of solving when you have undetermined systems. Okay. So let's do this in MATLAB. So A2 equals what, guys? A rows 1 to 2, everything. And B2 is going to be equal to B is 1 to 2, everything. You agree? So now if I do A2 backslash B2, do you see? The second element is 0, so it simply is ignored. The system is reduced to two equations, two unknown, and it's solved. However, if we do P inverse of A2 times B, oh, why is not supporting this one here? Oh, what I'm doing, it's not a dot, it's A2 P inverse, okay.
Is it because it's B and not B2? Or no?
Oh, yeah, you're completely right. Completely right. It's not B, it's B2. Yes. Thank you, Lauren. I was saying, what is going wrong with the mathematics here? No, simply mistake. Make sense? So these results here, guys, are like an OLS, but it's not based on sum of the square of the residuals. It's simply based on the Euclidean norm. So what you try to do is you try to minimize the diagonal of a matrix. Because remember, the diagonal, guys, is the one that controls the size of a matrix. Okay, how dispersed the matrix is depends basically on the diagonal. Got it? So let's talk a little about the Frobenius norm. Oh, wait a second. Before going there, in your Word document, you have this file. Can you copy this one here as a file? My system of equations A and B, an M file. You have this in the Word. Just copy this one here into MATLAB. My system of equations. And I want to see if I have it somewhere here. No, I don't have it. I'll open this. My system of equations.
Do you mind confirming once you're done the value you got with A2 backslash B2? Because I got an error for that. No, well, I got something like I got multiple matrices for that, so I'm not sure.
This one? P
The
inverse
one
of,
before that. The one before
oh,
that, please. Yeah.
this one. A2 backslash B2.
And
36,
then
0,
and
110.
110. I didn't let me check what I did wrong, but thank you.
Yeah. This one. Okay, guys, can you create your M file, save it, etc., and then before running, go line by line with this stuff here and try to run it. So remember, you need to provide, guys. So we have A and we have B. Yes. So you need to provide this one here. How do you run this system, guys? How do you run this program? You need two inputs, so you cannot run directly from here, correct? Because this program requires inputs, A and B. So what you're gonna do is you're gonna go copy this part here, go here, and then I don't have a small a, I have caps A and B, and then you run, correct? That's the way you run these programs. Okay? 1 minute to analyze this stuff, and then we do it together. I will stop, pause this one. Yes, I'm
Yeah, okay,
recording
okay.
now.
Okay,
Thank you.
got it. Thank
Okay, guys, so I need to give the inputs to my system, and it's going to return a matrix that is B. The name of my system is my system of equations, so in order to run, I simply enter here. So what I'm doing here is I'm verifying that A is correct and B is correct. Then N and M are simply the number of rows, number of columns. And nargin, guys, is simply that it checks if I provide only A, for example, not B, what nargin is going to check is simply number of arguments is not equal to 2. It's going to send me an error. You need an input. You need to input A and B. Got it? Simply an error message. Now, what this one is doing here, guys, is to check that the matrix is a square. Okay, so in this particular program, I'm not able to do over identified or under identified. Got it? I just want to be sure that A is a square matrix. So if N is not equal to M, error, matrix is not a square. This is not the case here. Okay, matrix A is not a square. So we can continue up to here. To move this one here. Continue. Okay. What is this one here controlling, guys? Is that sometimes the people V is entered as a row. Okay. And I want to be sure that if this happens, simply immediately I change it as a column. So this is what it's doing. If size of B2 is this is number of rows, number of columns is not equal to 1, simply shift it, transpose. Make sense? And then I compute the determinant. If determinant of A equals 0, so I'm simply checking for singularity. If determinant of A equals 0, I simply send a message, matrix is singular, and then I stop everything. Otherwise, I simply do what I have done, X inverse or X8 over B. Make sense to you guys?
Do you mind holding it for a second? Because
Yep.
the determinant one is not included on our document. Like
What?
yeah, those steps are not in the the singularity condition is not.
Okay, can you check that out? This is insane. Really?
Yeah. Yeah.
Yeah, it's not that. So I will copy this one here. This is insane. So this is the second time it's happened to me, this part here. I will copy in here just to have it correctly done. Yeah, so now we have it. Thank you. Okay, guys, and then you simply run. And then here you can see you're using your inverse or using the backslash. Okay? Make sense? Okay, so let's continue. So now let me save this one here for a minute. Now, guys, let's go into something. There is a way of finding the Frobenius norm. Okay, so let's create this one here. X equals 1, 2, 3. 1, 1, 2, 3, and 4. Okay, this is my X. Can you run simply? I don't know. Let's call pro. So what we can do is norm. So this is a Frobenius norm of X Frobenius. And the formula of this one here, guys, is equal to the square root of the diagonal of X prime X. No, I need to multiply. This is my quadratic. I need to, there is something more, of course. I need to sum this one here. So I'm summing all the diagonal elements of my quadratic, and then I'm taking the square root. So remember, I was telling to you guys that the dimension size is controlled by the diagonal. Okay. So what the Frobenius does, it simply calculates what is the distance in the diagonal. Remember, the distance is simply, you do the square. Do you remember if you have the distance between 2 points, you can have positives and negatives. So in order to avoid positives and negatives, what do? You square that. That's the distance. And then you sum all the distances. And then what do? You take the square root to go back to the original units. Correct? So this is the famous Frobenius norm. Can you? Okay, so test this one here. This is Fro comes from Frobenius. And then check that indeed the math works. Do it step by step. Just
What's the first number in the matrix?
in the matrix 1.
Okay.
Yeah. One. Okay, guys. So I said my x is going to be 1, 2, 3, 4, right? My x, no. Don't do anything here. So we'll close this one here. So my x equals 1, 2, 3, 4. Okay, so if I do norm x Frobenius, I have 5.4772. Okay, so this is the distance of the elements of the main diagonal. So now let's do I don't know. So let's call we can do this a equals x prime x. Okay. Then what I need to do is what, guys? I need to do the diagonal. Right? So I'm taking the elements of the diagonal. Then what I need to do is what? I need to sum. And then what I need to do, because what I have done is I have squared the elements of the main diagonal. So what I need to do is then what? Is QRT of this one here. Make sense? So everything is based on mathematics, guys. When we start doing optimizations, you're going to see that in that case, there is no closed form solutions. But up to now, everything is closed form solutions. So if you have a mathematical model, guys, you can just write it. Input data, and the model is going to run. Make sense? Can I call back my A? Okay, everyone is with me? There is one thing, guys, that is extremely important when we do matrix manipulations. Okay, it's called decompositions or transformations. One of them is what is called the eigenvalue. So I will explain you with examples. So let's do eigenvalue of A. I will explain what is an eigenvalue later mathematically. A couple of properties, guys. Do you remember what is a trace of a matrix? Do you remember what is a trace of a matrix, guys? It's simply the sum of the elements of the diagonal. Okay? So now let's call it R equal sum of D. Properties of the eigenvalues. The sum of the eigenvalues equals what? The trace. Now, you tell me this is what? 27. Can you take the determinant of A? 27. So two properties, guys, you need to remember. You're going to use these techniques later. The sum equals the trace, and the product of the eigenvalues equals the determinant. So that's another way of finding if there is a singularity in your matrix. And also, you have the rank. The rank is equal to the number of non-zero eigenvalues. So in this case, my rank is 3. So this implies that my matrix is non-singular because I have 3 independent rows or columns. Everything collapses to the same idea. Do you agree? Okay, so there is something more that is really interesting. This is eigen decompositions. Okay, so eigen decomposition. This is extremely powerful. You're gonna see in a minute. So this property holds, guys, is equal to BD. Okay, so what is V and D? So V and D are simply eigen of A. So this is my eigenvalues, eigenvectors, sorry. These are my eigenvectors. And these ones here are my eigenvalues. Okay, and this always holds. And you're going to see why this is extremely powerful, guys, in a minute. Okay, I will just give you the ideas. Tell me one thing, guys. I will make some operations here. Is this true? Right? I'm just moving to the other side. Now, what I will do is the following. AB times B minus 1 minus B, D, B minus 1. So I'm doing multiplying by B minus 1 at the end. This is right. This is correct, right? So from here, A, okay, so A minus B, D, B to the minus 1 should be equal to 0. Or if you want, yeah, that's okay. Do you agree with me? Oh, sorry. A, B, B, sorry. I have BDB, BDB, minus 1. Yeah, that's okay. What I can do is do this. So let me check. AB, BD, because they multiply. So yeah, this one is okay. Okay, guys, can you please verify that this is true? So run this with MATLAB and then verify that this is true and verify that this is true very quickly. And from here, we are going to run into something that is amazing in matrix multiplications and inverses and everything. So just prove this one here. So do this first, then prove this, and prove this one here. See what I have on here. No, loops, perfect. We're almost there, guys. Where is my MATLAB here? Okay, guys. So if I do BD equals eigenvalue of A, you see the eigenvalues. So these are the eigenvectors, and these are the eigenvalues. The eigenvalues are the ones that we found already. So each eigenvector, eigenvalue is related to its eigenvalue, eigenvectors. Each eigenvector, value eigenvector is linked to, so I cannot see this. The first column corresponds to this number here. The second column that is called an eigenvector corresponds to this number here. And the third column corresponds to this number here. And then the people say, why are we doing this decomposition? So is it useful or not? Yes, it is extremely useful. First of all, let's test A times B, correct? Is this equal to B times D? Yes, it is correct. Then I told you A minus B times D times B to the minus 1, sorry, minus 1 times B. Is this correct? Right? This is correct or not, guys? Yes, this is correct. You know, this is MATLAB. Do you know these numbers are 0? But take a look. MATLAB presents this as numbers because it's e to the minus 14. So technically, guys, it's not exactly equal to 0, but come on, it's 0. For economists, this is 0.
Quick question.
Yeah.
That first A, I have in my notes as A, V, and then V to the negative 1.
Yes.
Yeah.
Oh,
Or
no.
yeah.
I'm going directly to this last one.
Oh, you're skipping the last one. Okay.
Yeah, I'm just testing this one here.
Thank
Okay, and so why this is so important for the following? Okay, copy or do it. Everyone's with me. Now you want to see why this is important. Okay, take a look. I will do a little modification in here. I will go back to this one here and just follow me. AB equals BD, correct? So what I will do is I will do B times B minus 1 equals BD B minus 1. Agree with me? So I'm not modifying anything, but I know that this one here is an identity. So A should be equal to B, D, B to the minus 1. This one here, guys, makes your life in programming much simpler. No, not if you have a 4x4. If you have huge data sets, when you try to find the square of a matrix, the square root of a matrix, these ones here solve the issue in less than a second. Extremely powerful. Why? Take a look to this one here, guys. So what is equal to A times A? A squared, right? A times A, this is A squared. So let's do this. It's B, D, B minus 1 multiplied by B, D, B minus 1, correct? So if I multiply this one here is B, D, B minus 1 times B, D, B minus 1. So this is equal to I. This is B, D, D, B minus 1. Now, this is a diagonal matrix. Do you agree, guys? When you multiply a diagonal matrix, this indeed equals B, D squared, B prime, B minus 1. You see that? So in general, A to the n is going to be B, D to the n, B minus 1. Extremely simple. This is a very simple matrix. This is a very simple matrix. D is a diagonal. You simply square the numbers, and then you can find whatever you want. Got it? Can you try A squared? So do A times A, and then use this formula here to show me that they are exactly the same. So do A times A, and later do A squared equals B times D squared times B to the minus 1. Allow me 1 minute, guys. I need to bring water.
Yo, Lauren,
Yes.
when did class end on Monday?
8:25. 8:20.
Okay, it works, right? Should work. Okay, so let's go.
Yes, confirmed. Works.
Perfect. So basically, let's do 8 times, I don't know, it's 8 times 8. Okay, give me 1 second, guys. Dame 5 minutos. Okay. Okay. So I forgot that today is again the Knicks game. So we need to run. Okay, guys.
Let's run.
Yeah, hopefully we win this time. Yeah, last time was very, very good. I really enjoyed. Yeah, just in the limit. Okay, guys. So we're saying I get excited when I talk about basketball. What I was saying. Okay, got it. So this is this, right? So now what I need to do is I need to say B times D to the power 2 times inverse of B, right? And you can see, guys, exactly the same. Let me tell you guys why I'm showing you these techniques, because when you have in finance, unfortunately, we don't work with small data sets. We work with huge data sets. Got it? If you try to do the inverse, or you try to do this times this with a huge matrix, everything's going to collapse. This one here, the eigenvalue is very simple. The eigenvalue is simply matrix, very simple matrix manipulation. Then you get to your eigenvalues, and then from here you can go to wherever you want, square, cube. How do you imagine, guys, that is the inverse using the eigenvalues? Can I do the inverse using eigenvalues or not? What do you think?
Yeah.
Yeah, so, yeah. Take a look. It's very straightforward. Do you agree with me or not? You see my screen, right? Now, what if I do the inverse in here? I need to do the inverse also in here. Oh, sorry, no, not in here, not in the parentheses. Oh, yes, in here. Okay, so what is the inverse? So some notes here, guys. Let's say xy to the minus 1 is equal to y to the minus 1, x to the minus 1. Okay, this is one property. You need to shift the elements. So this is going to be, if I apply this one here, it's going to be b to the minus 1 to the minus 1, d to the minus 1. Let me move this part here. and b to the minus 1. Agree? So this moves here, etc. So a to the minus 1 is going to be a number to the minus 1. Minus 1 is the same number, right? Times b to the minus 1 times b to the minus 1. Take a look, guys. Exactly the same. Do you see? Okay, so let's test that. Can you test that indeed a to the minus 1 is equal to b, d minus 1, b minus 1?
Matrices stuff. Are you like raising it, make big matrices to like the 10th power and stuff like that?
Yeah,
Okay, so that's what, yeah.
yeah, exactly. So there are some mathematical models in which you go, I have gone to power 4,
Hmm.
okay, and try to find a power 4, let's say, just try one matrix that has 10,000 rows by 50 columns. The MATLAB is going to collapse for sure, okay? Just allow me 1 second, guys. Give me 1 second. Okay, have you tried that? So let's go into MATLAB. Am I recording? Yes. So inverse of A is this one here, right? What I can do is I can use the same as before, but instead of what I will do is d to the minus 1, and then you get it. Make sense, guys? The square root of a matrix, you can do that also. How do you think is going to be the square root of a matrix? Well, it is extremely fast. When you do dynamic models, guys, with a professor, who does dynamics in economics? Sean, is Philip Sean, or
Yeah, I think it is Professor Shaw. Yeah.
yes, Professor
Yeah.
Sean.
Yeah.
Yeah, he loves MATLAB, so you're going to work with MATLAB a lot. Okay, and he loves MATLAB because of that. So if you know some tricks in MATLAB, this runs extremely fast. Got it? Makes sense to everyone? And you can see here we have a very complex way of a complex solution, but it works in nothing. It takes no time. Questions, guys? Now I need to give you one more, and then with that one more, we are moving into loops. So what is called the singular value decomposition. Okay, the singular value decomposition, guys, is simply we're going to do USB is going to be equal to singular value decomposition of A. And the properties is the following, guys, that A is going to be equal to U times S times B. We're going to do applications of this singular value decomposition later, okay? Just prove that this is true, guys. okay? And just multiply U times S times B. What? Oh, US time. Oh my, yes, of course. Sorry, US time should be prime. Yes, it is prime here. Is USB the transpose of B? So we can recover the matrix. Okay, we're going to applications of this one later, guys. I prefer to run into the loops now. Oh, I gave you a couple of programs. Okay, so let's go to the simple one because I want to use the for loops as an example of a lot of things that we can make. So let me explain first how the for loops work. Okay, so the for loops, guys, have the following notation is for, let's
Wait,
say,
sorry. Before
yeah,
you continue on to for loops, do you mind if I
yep.
just get a screenshot of the singular value decom? The last slide.
This one?
No, on Paint, on Paint.
Oh, paint. Okay, so
Yeah,
I need to open, I think I need to open this one here. Yeah, I think this was the last one, right? Oh, yeah, don't save it. This
perfect.
one?
Thank you. Yes, thanks.
All this is recorded, guys. So you,
Oh, right. I forgot. Yeah, no,
no, but
I
you
got it.
can, but you
Yes.
got it? Perfect.
Yes. Thank you. Thank you so much.
Okay, so now let's go to new one. So I was telling to you how the for loops work. Okay, the for works in the following way. So you do for I equals, let's say 1 to 10, let's say. And then you are going to have an end. So the for loop always needs to finish an end. And you can do whatever you want inside. We're going to do a lot of things inside. Got it? So what I want from you guys is imagine, do you remember I want x to be equal to 1, 2, up to 10. Of course, we know how to do that, right? It's going to be equals 1, 1, 10. We can do that. But we can use also for loops. And in order to use the for loop, let's do the following, guys. Okay, I had for I equal 1 to 10. What MATLAB is going to do is going to find I equals 1, and I will tell them xi equals I. Do you see what I'm doing? Follow my logic. So it's going to be x1 is going to be 1, goes to the next one, x2 is going to be 2, etc. until it arrives to the last value. When it's 10, it's going to be x10 equals 10, goes one more, 11. Is 11 in my range? No, get out. Straightforward. Got it? Now, guys, recommendation. When you can do something in matrix form or sequence form, avoid for loops. Okay, there are some times in which we cannot avoid the for loops. But if you can avoid for loops, avoid them. Got it? Okay. So can you open, guys, an M file? Let's call loops. I think I created today in the afternoon one, but I didn't give it to you. Let's do this together. I think I can. I know I have done so many. Yeah, this one here. I think that in order to move faster, uh, I will copy this one here. Hopefully that the chat, do you think can work with that?
Yeah, probably.
Yeah, let's try. Yeah, can you copy this in your file and call it? And let's do this together. slowly because this is a very important one. I put this in the chat. Let me put this also in my.
What should we call this?
Loops.
Sure.
I think it's yeah, it's function loops.
Okay.
And this function, guys, is really, really, really important for us because it provides a lot of things that I want you to show. I want to show you. Oh, where's my? Okay, do you have it? Have you opened your function loops? Okay, perfect. So let's do it step by step. So this one here is the recommended way of doing sequences. Do you agree? But I will use loops only to show you how the things work. Okay, one thing that you always need to do, guys, is to start or initialize the variable. Okay, so what I'm doing here is one way that is less efficient of doing this stuff. So what I'm doing here, guys, is I'm initializing x1 to be zeros, 10, 1. So it's going to be zeros, 10 rows, 1 column. This is going to be full zeros. Do you agree? So that's why I show you zeros. Can you stop here? Let's run this one here. Where's my run? Yeah, change folder is okay. So you see my x1 is a vector full of zeros. And what I will do is I will start filling the zeros, changing the zeros by specific numbers. Got it? So this is one way of initializing vectors, guys. So then what I do is I simply start filling one by one. Let's do a couple of them. I equals 1 now. So if I can continue, take a look to x1. You see, it filled the first one with a number 1. So let's continue a little more. Take a look now. So it's 1, 2, etc., etc., etc. Make sense to everyone in the for loops? Okay, so let me move this one here and let's finish this one here. So I have x1, 1 to 10. Are you with me? Yep. The issue with this type of initialization, guys, is that I need to have the number of rows or columns that I need to have, 10, 20, 15. So this is kind of inefficient, do you agree? One way of not being, stopped by this number here is initializing your vector as an empty matrix. So what I'm saying is x5 is an empty matrix. Got it? And so take a look to how empty matrices work, because this is something we're going to be using all the time. Okay, I do the same. My for loop goes from 1 to 10. And then x5, so this variable here, is going to be equal to x5. So I need to put x5. And below this x5, use I. So what I will do at the beginning is empty, right? So what is going to be the first value? Empty with 1 is going to be the number 1. After you run this again, so your x5 now it contains only 1. Then you put the number 2, etc. So let's do that, and then you're going to see how this works. Okay, I think I choose no. Oh yeah, sorry, I ran too fast. I saved something here. Okay, so let's do this up to here. Yeah, x5 is empty. Do you see that? It's an empty matrix. Okay, let's do a couple of runs. So in the first one, x1 was empty, but now it has 1. So what is the dimension of x at this point, of x5? Is 1 by 1. Now I equals 2, so what I will do is I will add 2. Let's continue running. Take a look to the size of x5 now. You see the size is increasing 1 by 1. There is no limit to the size. So if you want to do 100 numbers, it doesn't matter. It will go to 100 numbers. It makes sense to you guys? This way of initializing a matrix is the most efficient way of initializing a matrix. You are not forced to have X number of rows. You can have as many rows as you want. It doesn't matter. It depends on your data. Make sense? Okay. Okay, so we can run. We can run this one. All right. Then I have my X5. That is going to be exactly the same. Okay. So now study this case, guys. Okay, just study this case. I will use the zeros 10 to 1. And what I just want is the first value to be 99. Okay, so I'm doing this one here just to show you how we can use for loops and if statements. Okay, take a look. Okay, I'm defining x2 equals zeros 10 to 1, 10 rows, 1 column. And then what I'm doing is I'm doing my loop, but I have an additional constraint that the first value should be equal to 99. So then what I'm doing is the following. If I equals 1, so remember it's a logic, so you need to have equal equals. Then what you do, x2i is going to be 99. Else, just continue with the numbering. So this is the way that if-else end condition works. Below I show you if-else conditions. But do you understand the way it works?
Yeah, are the indentations significant?
Yeah, you know what? I prefer to do the indentation, but you simply allow MATLAB you ask MATLAB to do this stuff here, you know?
Okay.
I prefer that because when you do code, I will show you at the end of the class, guys, one code that I think is the best baseline in the industry. It's not because I say it, because it's Nielsen that has said that. It has around 10,000 lines of code with additional, I think it's around 100 small subroutines. Okay. So imagine if it's not indented, it should be crazy, right? So indentation helps you to basically understand better what you're doing. Now, this for loop is indented with this one here, and you can collapse this one. Do you see that? You have the plus and minus. So if this is huge, you don't know where is finishing, you just collapse. And then you want to know basically, oh, it ends around 35, more or less. So then you can go and then look for 35 and you see where it ends. Make sense, guys? Okay, makes sense the way it works. The for loops is simply round, and then you have if conditions in between. Questions about this part here? So we can run up to here, and let's take a look to what happens with x2. You can see x2. It is exactly the same, but the first one with 99. That's all. Okay, so, oh yeah, here now I have the first and the last one. Okay, the first and the last one, 99. That's what I want. Okay, option one, the most logical one. Now, my if condition is going to have another logical. Remember, we have seen this logical, that means or. So what I'm telling MATLAB is, if I equals 1 or I equals 10, simply replace the position to value 99. Otherwise, simply do the sequence. Make sense to everyone? Okay, so let's go up to here. And then you can see your x3, 99 at the beginning, 99 at the end. Guys, these examples are toy examples, but you're gonna be seeing how useful they are when we work in real world. Ready? Okay, so the option two. So this is option two. So let me change this one here. So option two. Well, you know what? I did this one here to show you the condition, how is the conditional if, else if work. So take a look. Remember that in the previous example, I used the or condition here. In here, I will not use that, but because I want to show you the else if condition. Got it? Okay, so what I do is the following. If I equals 1, okay, x for I is 99. Then I have another condition, is else if. So this is when you add additional condition. You can add as many else if as you want, minus 1, because the last one needs to be else. Make sense to you? So the last condition must be else, guys. So what I'm doing is else if equals I equals 10. Okay, you do 99. Otherwise, you simply do the rounding up. So let's run this one here. Yeah, let me clean this one here. And here we go. It's the same result. Make sense to everyone? Yep. Okay. Allow me to stop this one here. Allow me to check I think I created something more. Yeah, initialization. Yeah, this is okay. We have done this stuff. Let me show you. No, not this one. B1. Yeah, okay. Okay, guys. So you are going to do this stuff. So what I want from you is I want to transform your variable, your model, I mean, your loop, and you're going to allow the input. So it's going to be starting and end, and you're going to provide, what is x? X1 and x2. What is x1? And x2. Oh, yeah, they are the same. Guys, what I want from you is simply to present 3 ways of doing the model. So you have your loops, right? These loops don't have anything. So you have here the numbers, 10, etc., etc., etc. So what I want is you to modify your program in such a way that you're going to accept 2 arguments. 1 for the starting point, 1 for the last point. Got it? And then you're going to return simply all your x's. X, x1, x2, x3, whatever. You can do, yeah. So you can use, guys, only up to here. Okay, so let's do loops. Can you copy all this one in a different file so we don't destroy this one? Let's open a new one. And the only thing that I'm interested is in, this is your x, this is your x2, and I will call this x2. This is going to be x2, it's going to be x2, and we don't need this stuff. So this is going to be your my loops B1. Okay, so you do it. Oh, no, loops. I will call it loops 2026 B1. Okay, guys. So the only thing that I want from you is that you enter. So someone is going. What I want to do is the following. Let's take a look. So in here, I want to run your program. I want X. Of course, all of them are going to be the same. X1 and X2. What is this one here? And this is going to be equal to your program. And I will enter 2 numbers. I want to start at 10 and to finish at 20. You see? So I should be clicking this one here, and your program should be providing me 10, 11, 12, 13, 14, 15, 16, 20. Got it? So then you need to be very careful, guys, because you need to find, well, this is my starting point, this is my end point. You just change all what are numbers into something that is different. So let's call S and D, start and end or whatever, S and D or no. Yeah, whatever letters you want, guys. Okay, 1 minute to do this. Do it, because sometimes we believe we know until we do it and we try it and then we don't do it. I'm pausing recording, so for record I will repeat what you think. So I have added two arguments, start and end, and I want to simply report three ways of presenting the same information, x, x1, and x2. X is very simple. It's a sequence that is going to start, let's say, for example, in 10, increasing by 1 up to 20. So this is simple. Then what I'm computing is the number of observations that I will have in my matrix is going to be number of observation knobs. E, let's say 20 minus 10 plus 1. So I have 11 observations. So my x1 is going to be zeros 11 times 1. Okay. So what I need to do now is replace position 1 with the number 10, etc. Agree? So, and that's where we are.
Would we use the sequence, like just the variable x?
Oh, no, but I don't want to
Oh.
use sequence. I want to use the for loops.
Oh, okay.
Just this one is easy. This one is done. What I want is to use for loops, guys. Think a little, okay? A couple of minutes to think. Let me stop this one here while you think. You need to find mathematical ways in which you do that. Perhaps you don't start at I1, you can start at 0, and then you simply reduce the number of observations, because if you start at 0, it's not going to go to 11, it's going to go to 10. And then you can do some sums around here, okay? Think a little. Okay, guys, so what we have said is that indeed we need to create something smart in here to capture what I want to generate. So what I'm doing here is I'm starting at S that is provided by the user. I'm adding I. So if it's I equals 1, the first time is going to be 1 minus 1 is 0. So it goes to 10, for example. If I equals 2, it's going to be 2 minus 1 is 1, plus 10, 11. If it's, let's say, 5, it's going to be 10 plus 5 minus 1 is 4, 14, etc. So you are going to be able to create your sequence using this technique here. Now, the difference between the definition of x1 as zeros and defining x2 as an empty matrix is that this one here already creates a space, uses a space. You are creating already a matrix full of zeros. So in terms of programming, this already is using a space. When you create an empty matrix, it is not using a space. So the most efficient way to do that is just creating an empty matrix, and then you start filling the values. Okay, so here is the same, x2, you start with x2 empty, and then you start adding, the first one is going to be 10, 1 minus 1 is 10, etc. And then you continue doing this stuff, and then we can get the results. So let's create D, stop the program at D, and let's see if this works. We have a problem. What is this problem here? Line 11. Where is my line 11? Oh, yes, of course, because I cannot run in this way. I need to provide the information here. Here we go. So let's take a look if everything is correct. Of course, this must be correct. Let's see x1, correct. And x2, correct. Makes sense? The only thing, guys, is that we have here rows and columns, okay? So perhaps we can define how do you want them to be provided, guys? Rows or columns?
I like columns.
Okay, yeah, me too.
Yeah.
So if it's columns, in that case, guys, the only thing that we need to do is this one, correct? Make sense? So everything is going to be in columns. Now, if you want to have this in rows like X, what you need to do, guys, is the definition of your zeros. Your zeros is going to be 1, instead of knobs 1, is going to be 1 knobs. Make sense to you? Guys, make sense? Everyone's with me?
Yes.
Now, what do we do in here when I have the empty matrix? What do I need to change? Because empty is empty. but I want the result to be not in a column, but in a row. What do I need to change?
Outside the brackets, you would just put the would you or no? Would you put I forget the name, not the apostrophe. Like the
Oh,
no.
yeah, I can do that. No, but no. That is going to create an issue to you because the next time you call, imagine, the next time you call your x is going to be a row. But next time you call your x is going to be a row, and you're going to imagine you have two observations, and then you're going to try to put one below. So it's going to collapse. Guys, simple. This one. This one here tells you just put down, 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 down. So instead of the semicolon, what I use is comma. And then it's going to put next, 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 next. Make sense to you guys? Okay, straightforward.
Yes.
Perfect. Okay, so it runs. So let's run this again just to be sure that everything is in a matrix form. Oh, what happened here? Wait a second. So what is this one here? Have I run this correct or no? Yeah. So why is not X being captured? Wait a second. Do I have another X somewhere here? Oh, sorry. I'm not running this. I'm running the old program. Yeah. So now it's not this one. No, it is this one. You need to save first the program, guys. Here we go. Okay. Okay. One final challenge for today. What I want is you to enter a start, end, and the increment. So now this one works when it's 1 by 1, correct? But what if I want to increase by 2? Make sense to you? So now what I want to run, so let's call this B loops B2, so it's just not destroying, we don't destroy our program. Let's call this one B2. Let me save this one here as a different name. B2. And then what I want, guys, is an additional factor, is increment. Okay, you know what? Just to make it more comparable to this one here, so let's do S, increment, and E. So let's do the first one with me. So this is going to be easy, right? Because this one here is simply the increment. So, and what I want to test is the following. So I want this to be 10 to 20. So I want this to be running my program. Okay, let's say 3-4 minutes. I will stop and please remind me to. Okay, so what I have done is I have not modified the number of observations. So the number of observations continue being 11. My x1 is going to be initially is going to be a 0s 11,1. And then what I do here is my increment is going to be I equals 1 to increment number of observation. It creates this matrix. So the numbers are correct, 10, 12, but I have a 0 in between. Got it? So what we can do to eliminate the zeros? Okay, guys. Okay, take a look to what happens here. So I have my x1 that has the zeros, etc. So, but I know that indeed, what I can do is I can jump these processes, right? So what if I do the following? Let's say that I will do an if condition. If my increment is not equal to 1, then what I can do, guys, I can define x1 as x1 from 1, I'm sorry, from 1 to increasing by increment to end. X1 is 1, comma 1. Okay, so you understand what I'm doing? Simply, you know that x1 contains the data, but it has zeros in between. What I want is to find the first position, the third position, etc. So take a look at what is happening here. This is going to be the first. So what this one is going to be doing is going to create 1, 3, 5, etc. So it's going to be selecting the ones that I'm interested in, yes or no. Okay, so let's try and test. So I want to stop here for a minute. Oh, it's not, doesn't run this way. Sorry. Should run here. Okay, so my x1, perfect. Now let's take a look to the sequence. I will copy the sequence in here. Oh, so it is 1 to 2 to n. N is 11 in this case. So it will provide me, I think, that information I want, right? It's going to take position 1, 3, 5, 7, and 11 from my sequence of xi's. Okay, so let's try. Yep, got it. Make sense to you guys? Now, this one here is coding. So coding, guys, you're not going to learn the coding. I'm giving you a lot of insights, etc. But the way you learn this stuff is by doing yourselves. By investing, 30 minutes on finding a solution that works like this. Make sense? And then this one works or not? X2. So let's try immediately. Yeah. You see another advantage, guys, of just defining this as an empty. Because an empty, you don't have this issue here. You are not addressing a matrix. You are simply putting the values as they appear. Make sense to everyone? Guys, make sense to everyone?
Yeah.
Okay?
Yes, Prof.
Perfect. So we stop here, guys. You have be working on your assignments. Better if you provide me your assignments with before the final, but I collect them for sure at all of them the last day of class when you present your projects. Next week, we're going to start talking already about projects, guys. If you have ideas, you want projects to work or anything that you plan to start working on, you just let me know so we can start talking and discussing about that. Okay? Remember, what I want from this class, guys, here is that you show me that you can use MATLAB. That you can get, I will show you next class how to get data, how to modify data from Excel or CSV or from the cloud. Got it? But that's the goal. Questions?
Yes, Prof. May I ask?
Yes.
So, with regards to the project, can it be that I collect data and then I use one of econometrics methods just to analyze the data, but
Yeah.
using MATLAB?
Yes, and also, and remember, you need to provide me, you use, subplots, plots. You just add things that you don't necessarily need, but show me that you know how to use MATLAB.
Okay.
Got it? So the idea is that, yes, you have your model, your mathematical model, econometric model. So you need to describe the model you're working. So you need to have a couple of pages describing what the model are, the equations, and then you go to the model. And in the model, you simply don't do what is exactly what you want, but just to show me, oh, I know how to use vectors, matrices, arrays, whatever. That's it.
Okay. Thank
Make
you.
sense?
Okay. Makes sense, Prof. Thank you.
Okay, guys. So see you on Monday then. If you don't have any more questions, take care, guys.
Thank you.
See you.
Bye-bye.
Bye-bye. Bye.
Good night.